Right now, as you listen to these words, the sun is converting 4 million tons of matter into pure energy every single second through nuclear fusion deep within its core. A process so energetically powerful that the light produced by a single fusion reaction will take more than 100,000 years to random walk its way from the sun's center to its surface before finally escaping into space and reaching Earth just 8 minutes later. This ancient light touching your skin right now began its journey as gamma radiation born in the sun's core during the Renaissance, gradually losing energy as it scattered through countless interactions with plasma and atoms, transforming from gamma rays to X-rays to ultraviolet to visible light, finally emerging from the sun's surface and crossing 93 million miles of empty space to reach you.
And here's what almost no one realizes. Every atom in your body, except for hydrogen, was forged inside a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created by nuclear fusion in stars that lived and died before our sun even formed. You are, quite literally, made of stardust. And the sun that lights your days and warms your world is itself a nuclear furnace, following patterns established billions of years ago. Patterns that will continue for billions more before the sun exhausts its fuel and transforms into something entirely different. Welcome. I'm glad you're here. This is a space dedicated to exploring the world's most fascinating facts in a calm, meditative way. A place where curiosity meets quietness, where profound truths become companions for drifting off. If you're new to these journeys, I'd be grateful if you'd subscribe and turn on notifications. These explorations continue because of listeners like you, and your presence here makes all the difference. Tonight, let's explore together the star at the center of our solar system, the source of nearly all energy on Earth, the object that has shaped every aspect of our world and our existence. Let's talk about the sun, not as a simple light in the sky, but as a massive, dynamic, incredibly complex sphere of plasma undergoing processes so extreme they seem almost impossible, yet following physical laws with such precision that we can predict its behavior millions of years into the future. The sun contains 99.86% of all mass in the solar system. Everything else, all 8 planets, their moons, the asteroids, comets, dust, and gas, together comprise less than 0.14% of the total. This staggering mass concentration means the sun's gravity dominates the entire solar system, holding planets in their orbits, controlling the trajectories of comets, determining the structure and dynamics of everything within its gravitational influence. At the sun's core, this immense mass creates crushing pressures, about 250 billion times Earth's atmospheric pressure, and temperatures around 27 million degrees Fahrenheit, conditions so extreme that hydrogen nuclei overcome their natural repulsion and fuse together, creating helium and releasing tremendous energy in the process. And here's what makes this nuclear fusion so remarkable. It's fighting constantly against the sun's gravity, trying to crush it. Gravity wants to compress the sun into a smaller, denser object. Fusion energy, in the form of heat and radiation pressure, pushes outward, supporting the sun against collapse. These two forces, gravitational compression inward and fusion pressure outward, balance almost perfectly, creating what's called hydrostatic equilibrium. This balance is dynamic and self-regulating. If fusion slows, the sun compresses slightly, increasing density and temperature in the core, which increases fusion rate. If fusion speeds up, the sun expands slightly, decreasing density and temperature, which decreases fusion rate. This negative feedback keeps the sun remarkably stable, maintaining nearly constant brightness and size over millions of years. Which brings us to understand something fascinating about the sun's structure and the journey energy takes from core to surface. The sun isn't uniform. It has distinct layers, each with different properties and behaviors. The core, where fusion occurs,
extends to about 25% of the sun's radius and contains more than half its mass. Temperature and pressure are highest here, and this is where virtually all the sun's energy originates. Surrounding the core is the radiative zone, extending to about 70% of the sun's radius, where energy slowly diffuses outward, carried by photons that are constantly absorbed and re-emitted by plasma, taking tens of thousands of years to cross this region. Beyond the radiative zone is the convective zone, where heat transport changes from radiation to convection. Hot plasma rises to the surface, cools by radiating energy into space, then sinks back down to be reheated. This convective motion creates the sun's granulation pattern, a cellular structure visible on the surface where each granule represents the top of a convection cell. Bright where hot plasma rises, darker between granules where cooler plasma sinks. These granules are enormous, typically about 600 miles across, yet they appear and disappear in just minutes, constantly churning as convection continuously renews the surface. And this leads to something equally remarkable about the sun's rotation. The sun rotates, but not as a solid body. Different latitudes rotate at different speeds because the sun is made of plasma, not solid material. The equator rotates fastest, completing a rotation in about 25 days, while the poles rotate more slowly, taking over 30 days. This differential rotation creates shear, adjacent regions moving at different speeds, which twists and tangles the sun's magnetic field, creating the complex magnetic structures that drive solar activity. The sun's magnetic field is generated by the dynamo effect. Moving conductive plasma in the sun's interior creates electrical currents, which generate magnetic fields, which influence plasma motion, creating a self-sustaining cycle. The field is complex and constantly changing, with field lines emerging from the surface, arcing through the corona and re-entering elsewhere. Where magnetic field lines are particularly strong and break through the surface, they create sunspots, darker regions that appear on the sun's visible surface. Sunspots appear dark because they're cooler than surrounding areas. Still about 6,500 degrees Fahrenheit, hot enough to glow if isolated, but several thousand degrees cooler than the surrounding photosphere at about 10,000 degrees Fahrenheit. The temperature difference makes them appear dark by contrast. Sunspots occur where strong magnetic fields suppress convection, preventing hot plasma from rising to the surface, creating cooler regions. Sunspots usually appear in pairs or groups, marking where magnetic field lines emerge from and return to the solar interior. But there's more to sunspots than just being dark patches. They vary in number and frequency over an approximately 11-year cycle called the solar cycle. At solar minimum, the sun may have no visible sunspots for weeks at a time. At solar maximum, dozens or even hundreds of spots may cover the surface simultaneously. This cycle reflects the systematic buildup and reversal of the sun's magnetic field. Over 11 years, the field becomes increasingly twisted and tangled, reaching a maximum complexity at solar maximum, then reorganizes with magnetic polarity reversed, beginning a new cycle. Two 11-year cycles comprise one complete 22-year magnetic cycle, after which the magnetic configuration returns to its original state. And here's what makes the solar cycle particularly important for Earth. Solar activity varies with it. Solar maximum brings more sunspots, but also more solar flares and coronal mass ejections, explosive events that can affect Earth's magnetic field, satellite operations, power grids, and communication systems. Solar minimum is quieter, with fewer disruptive events. This cycle was discovered by amateur astronomer Heinrich Schwabe in 1843, after 17 years of daily solar observations, a testament to patience and dedicated observation. Understanding the solar cycle allows some prediction of space weather, though the sun remains unpredictable in its details, capable of surprise even when following general patterns. Consider for a moment the timescales involved in solar phenomena. Granulation appears and disappears in minutes. sunspots evolve over days to weeks. The solar cycle operates on 11-year periods. The sun's fundamental structure and energy generation remain stable over millions of years. And the sun's overall lifetime, from formation to eventual death, spans 10 billion years. The sun exists across all these timescales simultaneously, each process operating at its own pace, all interconnected, all ultimately driven by the fundamental balance between gravity and nuclear fusion.
Which brings us to the question of the sun's age and life cycle. The sun formed about 4.6 billion years ago from the gravitational collapse of a region within a large molecular cloud, mostly hydrogen and helium left over from the Big Bang, plus heavier elements created by previous generations of stars. As the cloud collapsed, it fragmented, and one fragment became our solar system. The center of this collapsing cloud grew hotter and denser under gravitational compression until conditions allowed nuclear fusion to ignite. At that moment, the sun was born, a new star joining the hundreds of billions in our galaxy. For the past 4.6 billion years, the sun has been fusing hydrogen into helium in its core, steadily consuming its nuclear fuel while maintaining remarkable stability. But this cannot continue forever. The sun has consumed about half the hydrogen in its core, and in roughly 5 billion years, the core hydrogen will be exhausted. When that happens, the core will contract and heat up, allowing hydrogen fusion to continue in a shell around the inert helium core. This shell fusion will produce more energy than core fusion does now, causing the sun's outer layers to expand enormously. The sun will become a red giant, swelling to perhaps 100 times its current diameter, possibly engulfing Mercury, Venus, and possibly even Earth's orbit. And this leads to something both fascinating and sobering about Earth's long-term future. Long before the sun becomes a red giant, increasing solar luminosity will make Earth uninhabitable. The sun is gradually getting brighter, about 10% brighter than when it formed. Because as helium accumulates in the core contracts slightly to maintain fusion, which increases temperature and fusion rate. This trend will continue, and in about 1 billion years, the sun will be bright enough that Earth's oceans will boil away, creating a runaway greenhouse effect similar to what occurred on Venus. Life on Earth's surface will become impossible, though perhaps subsurface life might persist longer. Eventually, in about 7.5 billion years, the red giant sun will shed its outer layers, creating a planetary nebula, a glowing shell of gas expanding into space. What remains will be the exposed core, now a white dwarf, a dense, hot object about Earth-sized, but containing half the sun's mass. This white dwarf will slowly cool over billions of years, eventually becoming a black dwarf, a cold, dark remnant no longer producing energy. This is the sun's ultimate fate: transformation from main sequence star to red giant to planetary nebula to white dwarf to black dwarf. A process that will take trillions of years to complete. But there's more to the sun than just its eventual fate. Right now, the sun's outer atmosphere, its corona, presents one of solar physics' greatest mysteries. The corona is incredibly hot, millions of degrees Fahrenheit, much hotter than the visible surface below it at just 10,000 degrees Fahrenheit. This seems to violate thermodynamics, heat flowing from cooler to hotter regions. Something must be pumping energy into the corona, heating it to extreme temperatures. But the exact mechanism remains debated. Magnetic field interactions, wave heating, magnetic reconnection, all likely contribute, but understanding precisely how the corona reaches such high temperatures, despite being farther from the sun's core, is an active research area. The corona is visible during total solar eclipses, appearing as a pearly white halo around the blocked sun, with streamers and structures shaped by magnetic fields extending into space.
The corona gradually transitions into the solar wind, a continuous stream of charged particles flowing outward from the sun in all directions, filling the solar system. This solar wind travels at speeds ranging from 200 to 500 miles per second, carrying magnetic field and energy throughout the solar system, interacting with planets, comets, and the interstellar medium beyond. And here's what makes the solar wind particularly important for Earth. It shapes our magnetosphere and creates auroras. Earth's magnetic field deflects most solar wind around the planet, creating a protective bubble called the magnetosphere. But some solar wind particles enter the magnetosphere near the poles, where field lines converge. These particles spiral along field lines, eventually striking Earth's upper atmosphere, exciting atoms and molecules, causing them to emit light, auroras, the northern and southern lights. Auroras are direct visible evidence of solar wind interacting with Earth, beautiful displays created by invisible particles traveling from Sun to Earth. Which brings us to the phenomenon of solar flares and coronal mass ejections, explosive events that can dramatically affect Earth. Solar flares are sudden, intense bursts of electromagnetic radiation from the Sun's surface, associated with magnetic reconnection, when magnetic field lines break and reconnect in new configurations, releasing tremendous energy in the process. This energy accelerates particles, heats plasma, and produces radiation across the electromagnetic spectrum from radio waves to gamma rays. Large flares can disrupt radio communications, damage satellites, and increase radiation exposure for astronauts and high-altitude aircraft passengers. Coronal mass ejections, or CMEs, are even more dramatic. Billion-ton clouds of plasma and magnetic field ejected from the corona at speeds up to several million miles per hour. When a CME reaches Earth, typically 1 to 3 days after ejection, it can compress Earth's magnetosphere, induce electrical currents in power grids, potentially causing blackouts, damage satellites, and create intense auroras at lower latitudes than usual. The most powerful recorded geomagnetic storm, the Carrington event of 1859, caused auroras visible near the equator and induced currents strong enough to shock telegraph operators and set telegraph paper on fire. If a Carrington-scale event occurred today, it could cause trillions of dollars in damage to modern technology-dependent infrastructure. And alongside these dramatic events, there's the constant, subtle influence of solar radiation on Earth's climate and atmosphere. The sun is our primary energy source. Earth receives about 1,360 watts per square meter at the top of the atmosphere, a value called the solar constant. About 30% of this energy is reflected back to space by clouds, ice, and land. The remaining 70% is absorbed, warming the surface and atmosphere, driving weather systems, enabling photosynthesis, powering the water cycle, creating winds and ocean currents. Without the sun's energy, Earth would be a frozen, lifeless ball, its temperature near absolute zero, its oceans and atmosphere frozen solid on the surface. But there's more to solar influence than just the solar constant. Variations in solar output, even tiny fractions of a percent, can affect climate. The solar cycle causes approximately 0.1% variation in total solar irradiance between minimum and maximum. This small variation has measurable effects on Earth's atmosphere, though its influence on surface temperature is minor compared to other factors like greenhouse gas concentrations. More significant are long-term changes. During periods of reduced solar activity like the Maunder minimum from 1645 to 1715, when sunspots were extremely rare, Earth experienced slightly cooler temperatures, though natural climate variability and other factors also contributed. Consider for a moment how completely dependent Earth's life is on the sun. Every food chain begins with photosynthesis, plants converting sunlight into chemical energy stored in organic molecules. Herbivores eat plants, carnivores eat herbivores. Decomposers break down organic matter. But all energy ultimately traces back to sunlight captured by photosynthesis. Fossil fuels, coal, oil, natural gas, are ancient sunlight, stored by prehistoric photosynthetic organisms and preserved in geological formations. Wind energy comes from solar heating, creating temperature gradients that drive air motion. Hydroelectric power relies on the water cycle powered by solar evaporation. Even human body heat is solar energy processed through multiple trophic levels. The sun doesn't just light our days, it fundamentally powers the biosphere, enabling life's existence and persistence.
And this connects to something deeper about life's relationship with the sun. Life evolved under solar illumination, adapted to its rhythms, structured by its cycles. Circadian rhythms, internal biological clocks regulating sleep-wake cycles, and countless physiological processes, synchronized to the 24-hour day-night cycle created by Earth's rotation under the sun. Seasonal behaviors, migration, hibernation, breeding, flowering, respond to yearly cycles of solar illumination changing with Earth's axial tilt. Even evolution itself has been shaped by solar radiation. UV light causes mutations, some harmful, some neutral, some beneficial, contributing to genetic variation that natural selection acts upon. The sun is not just energy source, but evolutionary force, shaping life's development across billions of years. And as you rest here, your breathing slowing, your thoughts beginning to drift. Imagine the sun's light as a river of energy flowing from core to space, from sun to earth, from photosynthesis to food webs, from ancient forests to fossil fuels, from solar panels to electrical grids, powering everything, connecting everything, making possible the extraordinary complexity of life and civilization. That warmth you feel from sunlight isn't just heat. It's the direct touch of nuclear fusion occurring 93 million miles away. Energy that began as matter destroying itself in the sun's core, transforming through countless intermediate forms, before reaching you as gentle warmth on skin, as light allowing sight, as energy sustaining life. The sun gives constantly, abundantly, asking nothing in return, shining indifferent to whether we notice or appreciate, following the inexorable logic of physics and gravity and fusion, continuing its ancient work of converting mass to energy, darkness to light. The sun's surface, what we see when we look up during the day, is called the photosphere, a layer just a few hundred miles thick where the plasma becomes transparent enough for light to escape freely into space. Below this boundary, photons are constantly absorbed and re-emitted, trapped within the sun's dense interior. Above it, photons stream outward unimpeded, crossing the solar system at the speed of light. This relatively thin transition zone is what we perceive as the sun's surface, though there's no solid boundary, no distinct edge, just a gradual change in opacity where light begins its final journey outward. The photosphere has a temperature of about 10,000 degrees Fahrenheit, and its granulated texture, visible through solar telescopes as a pattern resembling rice grains, reveals the constant convective churning bringing hot plasma up and sending cooler plasma down. And here's what makes the photosphere's appearance even more dynamic. Limb darkening, where the sun appears brighter in the center and darker near its edges when viewed through proper filters. This occurs because when we look at the sun's center, we're seeing deeper, hotter layers, while near the edges, we're seeing only the cooler upper layers at an oblique angle. This effect demonstrates that the photosphere has structure, temperature and density varying with depth, and that the sun is three-dimensional, not a flat disk, even though it appears that way to our eyes. Which brings us to understand something remarkable about how we study the sun without being destroyed by it. Solar telescopes must deal with the sun's intensity. Concentrating sunlight can instantly incinerate equipment
or blind observers. Modern solar telescopes use sophisticated filtering, coronagraphs that block the bright disk to reveal the fainter corona, and instruments that observe in specific wavelengths, revealing different layers and phenomena. Some telescopes are ground-based, others orbit Earth above atmospheric interference, and a few spacecraft have approached the Sun directly, using heat shields to survive temperatures exceeding 2,500 degrees Fahrenheit while gathering unprecedented close-up data. The Parker Solar Probe, launched in 2018, is humanity's closest approach to the Sun, diving to within 4 million miles of the solar surface, closer than any previous spacecraft, traveling through the corona itself. At closest approach, the spacecraft experiences temperatures around 2,500 degrees Fahrenheit, but uses a carbon-carbon composite heat shield to protect its instruments, which remain at room temperature just inches behind the shield. Parker Solar Probe is measuring the corona's properties directly, studying how the solar wind accelerates, investigating magnetic fields, and trying to solve the coronal heating mystery through in-situ observations impossible from Earth.
And this leads to something equally fascinating about solar observatories on Earth and the techniques they use to watch the Sun continuously. Networks of solar telescopes around the world provide 24-hour coverage, ensuring the Sun is always observed somewhere despite Earth's rotation. Helioseismology, the study of oscillations and waves propagating through the Sun, allows scientists to probe the solar interior much like seismology reveals Earth's internal structure. The Sun rings like a bell, though at frequencies far below human hearing, with millions of different oscillation modes simultaneously present. By analyzing these oscillations' patterns and frequencies, scientists can determine temperature, density, composition, and rotation speed at different depths, effectively using sound waves to see inside the Sun.
But there's more to solar observation than just visible light and sound waves. The Sun emits radiation across the entire electromagnetic spectrum, and observing at different wavelengths reveals different phenomena. Radio observations track electron beams accelerated by flares. Ultraviolet and extreme ultraviolet imaging reveals the chromosphere and corona, showing temperatures from tens of thousands to millions of degrees. X-rays reveal the hottest plasma and most energetic events. Each wavelength provides a different window into solar processes, and combining observations across the spectrum creates a comprehensive picture of solar activity and structure. Consider for a moment the sophistication required to understand the Sun despite never touching it. We've never sent a sample return mission to the Sun. The heat and radiation would vaporize any spacecraft long before reaching the surface. And there's no solid surface to sample anyway. Everything we know comes from remote observation, from analyzing light and particles that reach us, from applying physics and mathematics to deduce what must be happening based on what we observe. Yet from this remote analysis, we understand nuclear fusion in the core, magnetic field generation in the interior, convection patterns, atmospheric dynamics, and evolutionary history spanning billions of years. This demonstrates science's power, to understand through observation and reasoning what cannot be directly experienced. And alongside understanding the present Sun, there's the question of how it compares to other stars. The Sun is remarkably average, a main sequence star of spectral type G2V, neither particularly large nor small, hot nor cool, bright nor dim. About 75% of stars in our galaxy are less massive than the Sun, mostly red dwarfs, small, cool, long-lived stars that burn their fuel slowly and can shine for trillions of years. About 25% are more massive, including the bright, hot, short-lived stars that dominate visible starlight, despite being numerically rare. The Sun sits comfortably in between, average in almost every measurable property, a typical star among the galaxy's hundreds of billions. This averageness has implications for life. Red dwarf stars, though common, present challenges for life. They're dim, requiring planets to orbit very close for warmth, which exposes planets to tidal locking and intense stellar flares. Massive stars burn too hot and die too quickly, living only millions of years rather than billions, insufficient time for complex life to evolve. The Sun's middle ground, warm enough to have a habitable zone at comfortable distance, stable enough to maintain consistent output, long-lived enough for evolution to produce complexity, may be optimal, or at least advantageous for life. If life is common in the universe, it might preferentially arise around Sun-like stars, rather than the more numerous but challenging red dwarfs or the brief-lived massive stars. Which brings us to the concept of the habitable zone. The range of distances from a star where liquid water could exist on a planet's surface, neither boiling away nor freezing solid. For the Sun, the habitable zone extends roughly from Venus's orbit to Mars's orbit, with Earth comfortably within it. The zone's boundaries are fuzzy. Depending on atmospheric composition and pressure, water could be liquid at different temperatures, expanding or contracting the zone. Venus, just inside the inner edge, experienced runaway greenhouse effect, becoming uninhabitable. Mars, near or just beyond the outer edge, lost its atmosphere and became too cold, though it may have been habitable early in solar system history when the Sun was slightly dimmer and Mars had thicker atmosphere. And here's what makes the habitable zone concept more complex. It changes over time. As the Sun ages and brightens, the habitable zone gradually moves outward. Early in solar system history, Venus might have been habitable while Earth was marginal. In the distant future, Earth will become too hot, while Mars might briefly become habitable before the Sun's red giant phase renders the entire inner solar system uninhabitable. The habitable zone is not static, but evolves with stellar evolution, creating windows of habitability that open and close over billions of years. But there's more to habitability than just temperature and liquid water. Stellar activity, flares, CMEs, energetic particle events, can strip planetary atmospheres, sterilize surfaces with radiation, and disrupt complex chemistry necessary for life. Young stars, including the young Sun billions of years ago, are more active than older stars, potentially making life's emergence more difficult despite having suitable temperatures. The Sun's gradual calming over time, combined with Earth's protective magnetic field and atmosphere, created increasingly favorable conditions for life's development and diversification. And this leads to something equally fascinating about how the Sun has changed over Earth's history and how life adapted. The young Sun was about 30% dimmer than today, yet Earth wasn't frozen. Geological evidence shows liquid water existed 3.8 billion years ago. This faint young Sun paradox suggests Earth's early atmosphere was different, perhaps with higher concentrations of greenhouse gases like methane or carbon dioxide, keeping the planet warm despite reduced solar input. As the Sun brightened and these greenhouse gases decreased, partly through biological processes like photosynthesis, temperature remained relatively stable, creating the narrow, habitable window that persisted billions of years. Photosynthetic organisms transformed Earth's atmosphere, producing oxygen as a waste product, gradually building up oxygen concentration from near zero to current levels around 21%. This oxygen enrichment, called the Great Oxidation Event about 2.4 billion years ago, was one of Earth's most dramatic environmental changes, enabling the evolution of complex multicellular life that requires oxygen for energy-intensive metabolism. The Sun provided the energy. Photosynthesis converted it to chemical form while releasing oxygen, and life was able to harness that oxygen for more efficient energy production. The Sun didn't just enable life, it enabled life's transformation of the planet, creating conditions for its own further evolution. Consider for a moment the elemental composition of the Sun and what it reveals about cosmic history. The Sun is about 73% hydrogen and 25% helium by mass, with remaining 2% consisting of heavier elements: oxygen, carbon, nitrogen, iron, and dozens of others. This 2% is cosmically significant. In the immediate aftermath of the Big Bang, only hydrogen, helium, and trace lithium existed. Every heavier element was created later inside stars through nuclear fusion and released into space when stars died, either through gradual mass loss or explosive supernovae. The Sun formed from a molecular cloud already enriched with these heavy elements from previous stellar generations. Our existence depends on this enrichment. Without elements like carbon, nitrogen, oxygen, and iron created by earlier stars, rocky planets and life wouldn't be possible. This makes us literally children of stars, not metaphorically, but physically. The atoms composing our bodies, the elements in Earth's crust, the metals in our technology, all were synthesized in stellar interiors billions of years ago, ejected into space, incorporated into new star systems, including ours. We are recycled stardust, matter that has cycled through cosmic processes spanning the universe's history, temporarily assembled into forms we call planets and life, before eventually dispersing and recycling again when the Sun dies and returns its material to interstellar space for future generations of stars and planets. And alongside this cosmic perspective, there's the immediate, personal experience of the Sun. Its warmth on skin, its light revealing color and form, its daily cycle structuring time and activity. Humans are profoundly solar creatures. We evolved under sunlight, adapted to its rhythms, dependent on its energy. Sunlight triggers vitamin D synthesis in skin, essential for health. Sunlight regulates circadian rhythms through specialized cells in the retina that detect blue light and synchronize internal clocks. Exposure to sunlight affects mood. Seasonal affective disorder during winter months reflects reduced sunlight's psychological impact. Even our aesthetic appreciation, finding sunrises and sunsets beautiful, preferring sunny days, enjoying warmth, reflects deep evolutionary adaptation to solar cycles. Which brings us to the cultural and religious significance of the Sun across human civilizations. Nearly every ancient culture revered the Sun as deity, as symbol of power and life, as object of worship and sacrifice. Egyptian Ra, Greek Helios, Aztec Tonatiuh, Japanese Amaterasu. Countless cultures personified the Sun, attributing consciousness and will to it. Solar temples aligned to solstices and equinoxes marked Sun's apparent motion through the year. Agricultural societies structured calendars around solar cycles, knowing planting and harvest times depend on seasonal sunlight changes. Even modern secular societies mark summer and winter solstices, celebrating the extremes of the Sun's annual journey across the sky. But there's more to solar mythology than just reverence. Stories explaining solar eclipses, dragons eating the sun, gods battling in the sky, reflect how unexplained phenomena inspire narrative creation. Myths about solar deities often involve daily journeys across the sky, nighttime journeys through underworld, battles with darkness, metaphorical representations of the day-night cycle that structured human experience long before scientific understanding. These myths served functions, explaining the inexplicable, providing moral frameworks, uniting communities through shared beliefs. They represent humanity's attempt to understand and relate to the most visible, most important celestial object affecting daily life. And this leads to something equally fascinating about how solar observations contributed to scientific revolution. Tracking the sun's motion led to understanding Earth orbits the sun, rather than vice versa. A transformation in worldview so significant it triggered religious and philosophical upheaval. Galileo's observation of sunspots contradicted ideas about celestial perfection, demonstrating the sun changes and has features. Understanding sunlight's spectrum revealed the sun's composition, demonstrating that celestial and terrestrial matter follow same physical laws. Solar physics became a testing ground for fundamental physics, spectroscopy, quantum mechanics, nuclear physics, all applied to understanding how the sun works, then generalized to understanding physics universally. The sun thus played dual roles in intellectual history. First as object of wonder and worship requiring mythological explanation, then as object of study demonstrating scientific methods' power. This transition from mythology to science didn't eliminate wonder, but deepened it, replacing simple stories with profound understanding of how matter converts to energy, how gravity balances pressure, how magnetic fields twist and reconnect, how nuclear fusion powers stars across the universe. The sun remains wonderful, but now we understand why. Not because gods command it, but because physics dictates it, following laws elegant and universal, demonstrating that nature operates through comprehensible principles. And as you drift deeper into rest, your thoughts dissolving like morning mist under rising sun, reflect on how intimately connected you are to that distant sphere of plasma. Every breath you take releases carbon dioxide that plants will convert back to oxygen using sunlight. Every movement you make runs on energy that originated as fusion in the sun's core, captured by photosynthesis, passed through food chains to reach you. Every warm day, every lit room with windows, every color you see, all gifts of sunlight, direct or indirect. The sun doesn't know you exist, doesn't care about human concerns, simply continues its ancient pattern of burning hydrogen, converting mass to energy, shining indifferently yet abundantly, making possible everything we know and experience. Tomorrow it will rise again, as it has for billions of years, as it will for billions more, constant companion to Earth, life's enabler, light in the darkness. The sun's energy output is staggering in its magnitude. Approximately 3.8 times 10 of 6,000 watts, or 380 septillion watts, every single second. To put this in perspective, the sun produces more energy in 1 second than all of human civilization has produced in its entire history. Earth intercepts just 1/billionth of this total output, a tiny fraction. Yet this minuscule sliver is enough to power all weather systems, ocean currents, photosynthesis, and the entire biosphere. The vast majority of the sun's energy radiates into space, spreading outward in all directions, eventually contributing to the thermal radiation background of the universe. This extravagant waste, from a human perspective, is simply how stars work. Fusion produces energy that must escape, and the sun has no way to direct it, no mechanism to concentrate it. It simply shines in all directions, illuminating the solar system and beyond. And here's what makes this energy production even more remarkable. It's sustained by converting a remarkably small amount of mass. Einstein's famous equation, E equals mc squared, relates energy to mass through the speed of light squared. A huge number, meaning small amounts of mass contain enormous energy. The sun converts about 4 million tons of mass into energy every second. Yet the sun is so massive, containing about 333,000 Earth masses, that this loss is negligible. At current conversion rates, the sun will lose only about 0.03% of its mass over its entire main sequence lifetime. It's burning itself, consuming its own substance to produce light. Yet it's so enormous that this self-consumption can continue for billions of years before exhausting its fuel. Which brings us to understand something fascinating about the specific fusion process occurring in the sun's core. The proton-proton chain reaction dominates, a sequence where hydrogen nuclei, protons, fuse through multiple steps to eventually create helium, releasing energy at each step. The initial step requires 2 protons to collide with sufficient energy to overcome electromagnetic repulsion. Protons are positively charged and naturally repel each other. Only the extreme temperatures and pressures in the core allow this to occur, and even then, quantum tunneling is required. Protons can occasionally tunnel through the repulsive barrier in ways forbidden by classical physics but permitted by quantum mechanics. Once two protons fuse, one immediately converts to a neutron through beta plus decay, releasing a positron and neutrino, creating deuterium, heavy hydrogen with one proton and one neutron. This deuterium then fuses with another proton, creating helium-3. Two helium-3 nuclei eventually collide and fuse, releasing two protons and creating helium-4, the stable helium nucleus. The net result? 4 hydrogen nuclei become one helium nucleus, releasing energy primarily as gamma-ray photons and neutrinos. The gamma rays are immediately absorbed by surrounding plasma, their energy gradually thermalized, degraded into lower energy photons and kinetic energy of particles. The neutrinos, however, barely interact with matter and escape directly from the core, streaming through the sun's outer layers as if they weren't there, reaching Earth just 8 minutes after their creation. And this leads to something equally remarkable about solar neutrinos and what they reveal. Neutrinos are ghost-like particles. They have almost no mass, no charge, and interact so weakly with matter that trillions pass through your body every second without any interaction. Detecting them requires massive, sophisticated detectors deep underground, shielded from cosmic rays and other interference. When solar neutrino experiments began detecting these particles in the 1960s, they found only about 1/3 the expected number, a discrepancy that persisted for decades, creating the solar neutrino problem. This problem was eventually resolved by discovering that neutrinos oscillate. They change between 3 different types, or flavors, as they travel. Solar fusion produces electron neutrinos, but by the time they reach Earth, some have oscillated into muon or tau neutrinos. Early detectors only detected electron neutrinos, explaining the apparent deficit. This discovery had profound implications, demonstrating that neutrinos have mass, even if extremely small, and confirming predictions of particle physics in unexpected ways. Solar neutrino detection thus serves dual purposes, confirming that fusion occurs in the sun's core and advancing fundamental physics understanding. But there's more to solar energy than fusion in the core. The energy must travel from core to surface, and this journey involves fascinating physics. In the radiative zone, energy moves through radiation, photons bouncing from particle to particle in a random walk, gradually working their way outward. A photon might travel a few millimeters before being absorbed, re-emitted in a random direction, absorbed again, re-emitted countless times. The path is so circuitous that photons take tens of thousands to hundreds of thousands of years to cross the radiative zone, even though traveling at the speed of light. This creates an enormous thermal mass. The sun's interior contains vast amounts of energy in transit, enough that if fusion suddenly stopped, the sun would continue shining at nearly current brightness for millions of years before that stored energy escaped. In the convective zone, energy transport changes to convection. Hot plasma physically rises, transporting energy upward, while cooler plasma sinks. This convective motion is turbulent and chaotic, creating the granulation pattern visible on the photosphere. Each granule represents one convection cell, hot plasma rising in the center, spreading outward, cooling by radiating energy, then sinking at the granule edges. Larger-scale convection cells, called supergranules, span tens of thousands of miles and persist for about a day. Even larger structures, giant cells, may exist, though they're difficult to detect directly. This hierarchical convection, operating at multiple scales simultaneously, efficiently transports energy the final distance to the surface where it radiates into space. Consider for a moment the violence of the solar surface when viewed in detail. Time-lapse observations reveal a boiling, churning cauldron, granules constantly appearing and disappearing, plasma flowing in complex patterns, magnetic fields emerging and colliding, energy releasing in flares and eruptions. The photosphere is not a calm, static surface, but a dynamic boundary layer where hot material from below meets the vacuum of space, where turbulence and magnetism create ever-changing structures. The smooth, serene disk we see from Earth conceals incredible complexity, violence, and energy, hidden by distance but revealed through telescopic observation. And alongside surface convection, there's the chromosphere, a thin layer just above the photosphere, visible as a reddish glow during solar eclipses. The chromosphere is hotter than the photosphere beneath it, temperatures rising from about 10,000 degrees Fahrenheit to 40,000 degrees Fahrenheit with altitude. Another manifestation of the coronal heating problem. The chromosphere has structure, spicules, jet-like features about 600 miles wide and 6,000 miles tall, constantly forming and dissolving, carrying mass and energy from the photosphere into the corona. Tens of thousands of spicules cover the sun at any moment, creating a forest of plasma jets continuously feeding material into the outer atmosphere. Which brings us to the prominences and filaments that arc above the solar surface. Enormous loops and sheets of plasma suspended by magnetic fields. When viewed against the bright disk, these features appear dark and are called filaments. When seen projecting beyond the limb during eclipses or through coronagraphs, they appear bright and are called prominences. These structures can be enormous. Some extend hundreds of thousands of miles into space, dwarfing Earth in size. They can persist for weeks or months, slowly evolving as magnetic fields shift and twist. Sometimes they become unstable and erupt, ejecting billions of tons of plasma into space in spectacular coronal mass ejections that, if directed at Earth, can trigger geomagnetic storms and auroras. And this leads to something equally fascinating about the sun's magnetic field and its role in solar activity. The field originates from the dynamo process in the convective zone, but it doesn't remain confined internally. Field lines break through the surface, creating complex structures that control much of what we observe. Sunspots mark where field lines emerge and return. Coronal loops trace field lines threading through the corona. Solar flares occur when field lines reconnect, suddenly releasing magnetic energy. The entire pattern of solar activity, sunspot cycles, flare frequency, CME occurrence, reflects the underlying magnetic field's evolution. But there's more to magnetic fields than just creating visible structures. They also store enormous amounts of energy. Magnetic fields in sunspot regions can be thousands of times stronger than Earth's magnetic field, containing energy densities comparable to the kinetic energy of plasma motion. When these fields become twisted and stressed through differential rotation and convective motion, they store increasing energy, much like a rubber band twisted tighter and tighter. Eventually, the field configuration becomes unstable, reconnects in a lower energy configuration, and explosively releases the stored energy as flares and CMEs. This cycle of energy buildup and release drives most transient solar phenomena. And alongside magnetic activity, there's the solar wind's acceleration mechanism, still not fully understood despite decades of study. Somehow, the corona's hot, diffuse plasma accelerates to supersonic speeds as it flows away from the sun. Thermal pressure alone cannot account for this acceleration. Calculations show that if solar wind were purely thermally driven, it would expand much more slowly and wouldn't achieve observed speeds. Something must add energy to the accelerating wind. Magnetic fields likely play a role. Alphen waves, magnetic oscillations propagating through plasma, might deposit energy. Magnetic reconnection in the corona might contribute. The Parker Solar Probe is gathering data directly in the acceleration region, finally providing in situ measurements to constrain theories. Consider for a moment the solar wind's reach. It flows continuously outward, past all the planets, creating a bubble called the heliosphere. the region where solar wind dominates over interstellar medium. The heliosphere extends well beyond Pluto's orbit, perhaps 100 astronomical units or more, depending on direction and solar activity level. At the heliosphere's boundary, the heliopause, solar wind pressure balances interstellar pressure, creating a termination shock where wind suddenly slows from supersonic to subsonic. The Voyager spacecraft crossed this boundary in 2012 and 2018, becoming the first human-made objects to enter interstellar space, though they remain within the Sun's gravitational influence and will for tens of thousands of years. Which brings us to the question of the Sun's position in our galaxy and its motion through space. The Sun orbits the galactic center, the supermassive black hole at the Milky Way's heart, at a distance of about 26,000 light-years, taking roughly 225 million years to complete one orbit. This galactic year defines a timescale much longer than human civilization. The last time the Sun was at its current galactic position, dinosaurs had not yet evolved. The Sun isn't fixed in its orbit, but oscillates above and below the galactic plane, currently passing through the plane while moving northward. These orbital dynamics expose the solar system to varying conditions, different radiation environments, different stellar densities, potentially different comet populations, that might influence Earth's climate and evolutionary history over tens of millions of years. And alongside orbital motion, there's the Sun's motion relative to nearby stars. The Sun moves at about 12 miles per second relative to the local standard of rest, the average motion of nearby stars. This motion carries the Sun and its planets through the local interstellar medium, encountering clouds of gas and dust that might periodically enter the heliosphere, potentially affecting Earth's climate through complicated mechanisms still being investigated. The Sun is also moving toward the constellation Hercules, the solar apex, at about 43,000 miles per hour relative to nearby stars. This motion will gradually change the night sky's appearance over thousands of years as the Sun moves among the stars, shifting our perspective on the galaxy. But there's more to the Sun's galactic context than just motion. The Sun exists in a relatively sparse region called the local bubble, a cavity in the interstellar medium about 1,000 light-years across, cleared by supernova explosions millions of years ago. The bubble's interior has low gas density and higher temperature than typical interstellar space, possibly affecting the heliosphere's shape and the solar wind's interaction with interstellar medium. The Sun also resides in the Orion Arm, a minor spiral arm connecting two major spiral arms. We're not in the galactic center, not in a major spiral arm, but in a relatively quiet suburban neighborhood of the galaxy, perhaps advantageous for life, avoiding the radiation and gravitational disruptions of more active regions. And this leads to something equally fascinating about how the Sun compares to other stars in terms of stability and habitability. The Sun shows relatively low variability compared to many stars. Some stars exhibit dramatic fluctuations, variable stars that regularly brighten and dim, flare stars with frequent powerful outbursts, binary stars with complicated light curves from mutual eclipses and tidal interactions. The Sun is comparatively calm, maintaining steady output with only small variations associated with the solar cycle. This stability has persisted billions of years, providing consistent conditions that allowed life to evolve without catastrophic interruptions. If the Sun were highly variable, life's emergence and persistence might have been impossible. Constant, dramatic environmental changes preventing the gradual evolution of complexity. And as you rest here, your thoughts drifting like light scattering through plasma, imagine the Sun's core, that tiny region at the center where 4 million tons of matter become energy every second, where temperatures reach 27 million degrees, where the crushing pressure of 250 billion atmospheres forces hydrogen nuclei together despite their electromagnetic repulsion, where quantum mechanics allows the impossible to occur, where the energy sustaining all life on Earth is born in nuclear fire. That core has been burning for 4.6 billion years, will burn for 5 billion more following the same process. The same fusion reactions, moment after moment, year after year, eon after eon. Constant and reliable, converting mass to light, hydrogen to helium, supporting the sun against its own gravity, maintaining the balance that allows life on Earth to flourish.
The sun is patient, persistent, inevitable. A natural machine operating according to physics, indifferent yet essential, distant yet intimate, strange yet familiar, alien yet the very source of home. There are moments in Earth's history when the sun's influence becomes suddenly, dramatically apparent. Not through its steady illumination, but through its disruptions. In March 1989, a massive coronal mass ejection struck Earth's magnetosphere, compressing it violently, inducing electrical currents in power grids across North America. In Quebec, transformers overloaded and tripped offline in a cascading failure that plunged 6 million people into darkness in just 90 seconds. Auroras danced in the skies as far south as Texas and Florida, beautiful manifestations of the same magnetic storm that crippled infrastructure. This event demonstrated our technological civilization's vulnerability to solar activity, a reminder that, despite our apparent mastery of Earth, we remain subject to forces originating 93 million miles away, that the sun can reach across space and touch our world in ways both spectacular and destructive. And here's what makes space weather particularly concerning for modern civilization. Our dependence on technology, vulnerable to electromagnetic disturbances, has increased dramatically. Satellites providing GPS navigation, communications, weather monitoring, and military surveillance orbit in regions exposed to energetic particles from solar storms. These particles can damage solar panels, degrade electronics, and interfere with sensors. Power grids with long transmission lines are vulnerable to geomagnetically induced currents that can damage transformers. Expensive, difficult-to-replace components that take months or years to manufacture. High-frequency radio communications depend on the ionosphere, which solar storms can disturb, causing blackouts. Even pipelines and railways, through their conductive infrastructure, can experience induced currents affecting operations. Which brings us to understand something remarkable about efforts to predict space weather and mitigate its impacts. Solar observatories continuously monitor the sun, watching for flares and CMEs. When an Earth-directed CME is detected, models predict its arrival time, typically 1 to 3 days after eruption, and estimate its strength and potential impacts. This advance warning allows satellite operators to put spacecraft in safe modes, power grid operators to reconfigure systems to minimize vulnerability, airlines to reroute flights away from polar regions where radiation exposure increases during storms, and astronauts on the International Space Station to take shelter in more heavily shielded modules. But prediction remains imperfect. The sun's complexity and chaotic nature make precise forecasting difficult. We can identify when the sun is particularly active, when CMEs occur, and roughly estimate their trajectories. But predicting exactly which regions will be affected and how severely requires better understanding of solar physics and magnetospheric dynamics. Space weather forecasting is where weather prediction was decades ago. Useful but limited, providing general warnings rather than precise predictions. Improving these forecasts requires better observations, more sophisticated models, and continued research into the fundamental processes generating solar activity. And this leads to something equally fascinating about solar storms of the past, and what they reveal about the sun's potential fury. Tree rings and ice cores contain records of solar activity through cosmogenic isotopes, carbon-14 and beryllium-10, produced when cosmic rays strike Earth's atmosphere. During active solar periods, the stronger solar wind shields Earth from cosmic rays, reducing isotope production. During quiet periods,
more cosmic rays reach Earth, increasing isotope production. These records extend thousands of years, revealing variations in solar activity far longer than direct observations.
Analysis of these records reveals occasional extreme events. In 774 CE and 993 CE, carbon-14 levels spiked dramatically, suggesting solar storms far more powerful than anything recorded in modern times. These events would have been inconsequential for medieval societies without electrical technology. But if equivalent storms occurred today, they could cause catastrophic damage. Continent-wide power blackouts lasting months, permanent satellite damage numbering in the hundreds or thousands, disruption of communications and navigation systems worldwide, economic losses potentially in the trillions of dollars. The probability of such extreme events is low in any given year, but accumulates over decades and centuries, representing a black swan risk, rare but potentially devastating. Consider for a moment the irony that the sun, source of all comfort and life on Earth, also poses existential risks to technological civilization. We've built infrastructure optimized for normal conditions, inadequately prepared for rare extremes. This isn't unique to space weather. We face similar challenges with earthquakes, floods, pandemics. But space weather has the potential for simultaneous global impact, affecting entire hemispheres rather than localized regions. Preparing for low-probability, high-impact solar events requires investments in grid hardening, satellite shielding, backup systems, and forecasting capabilities. Costs that compete with other priorities, but represent insurance against potentially civilization-altering disruptions. But there's more to the sun's influence on Earth than electromagnetic storms. Solar activity affects Earth's atmosphere and climate through subtle, complex mechanisms still being investigated. The solar UV output, ultraviolet radiation, varies more strongly with the solar cycle than total solar irradiance, changing by 10% or more between solar minimum and maximum. This UV variation affects the stratosphere, particularly ozone chemistry and temperature structure, which can influence atmospheric circulation patterns that propagate to the surface, potentially affecting weather. The mechanisms are complex and not fully understood, making it difficult to quantify solar activity's contribution to climate variability, but evidence suggests it plays a role, though smaller than anthropogenic factors like greenhouse gas emissions. And alongside direct radiation effects, there's the role of cosmic rays, modulated by solar activity. Cosmic rays, high-energy particles from supernovae and other galactic sources, constantly bombard Earth's atmosphere, creating ionization. Solar activity affects how many cosmic rays reach Earth. Stronger solar wind during active periods provides better shielding, reducing cosmic ray flux. Some researchers hypothesize that cosmic rays influence cloud formation by providing ionization nuclei, potentially linking solar activity to cloudiness and thus to climate. This hypothesis remains controversial and lacks definitive evidence, but it illustrates how subtle connections between the sun and Earth might exist beyond obvious heating and lighting. Which brings us to the question of how unusual our sun is, and what this means for life in the universe. As mentioned earlier, the sun is remarkably average, a G-type main sequence star, neither particularly massive nor small, metal-rich compared to older stars, but not exceptionally so, rotating at typical rates, showing typical activity levels. This averageness might be advantageous. More massive stars live shorter lives. O and B-type stars shine brilliantly but burn out in millions of years, insufficient for complex life to evolve. Red dwarfs live trillions of years but are dim, requiring planets to orbit very close, exposing them to tidal locking and flare activity. The sun occupies a Goldilocks zone of stellar properties, massive enough for planets to form and for fusion to last billions of years,
but not so massive that it dies before life evolves.
And this leads to something equally fascinating about the search for habitable planets around other stars. Thousands of exoplanets have been discovered, many around stars similar to the Sun. Some orbit in their stars' habitable zones where liquid water might exist. But habitability depends on many factors beyond temperature: atmospheric composition, magnetic field strength, geological activity, stellar stability, cosmic environment. A planet in the habitable zone of a flare star might be sterile, its atmosphere stripped by frequent energetic eruptions. A planet with no magnetic field might lose its atmosphere to stellar wind. A planet with no plate tectonics might lack the carbon cycle that stabilizes climate. The Sun-Earth system represents one successful configuration, but we don't yet know how common such configurations are, or what range of variation still permits life. But there's more to the question of life around other stars than just planetary conditions. The galactic environment matters too. Regions near the galactic center experience higher radiation levels, more frequent supernovae, and stronger tidal forces, potentially disrupting planetary orbits. Regions in the galactic halo have low metallicity, few heavy elements, making rocky planet formation difficult or impossible. The Sun orbits in the galactic habitable zone, the region where conditions favor stable planetary systems with long-lived stars and low external threats. This adds another layer to the question of life's commonness. Not just do planets exist in stellar habitable zones, but do those stars exist in galactic habitable zones? Consider for a moment what it means that the Sun, average and unremarkable among hundreds of billions of stars, created conditions for life that asks these questions. The chain of circumstances seems improbable. A molecular cloud enriched with heavy elements from previous stellar generations, collapsing to form a star of just the right mass, with planets forming at appropriate distances. One planet maintaining liquid water for billions of years. Life emerging and evolving toward complexity, eventually producing consciousness that can study the Sun and ponder its place in the cosmos. Yet this improbable sequence occurred at least once, demonstrably, because we exist to observe it. Whether it's common or rare, inevitable or miraculous, remains one of science's deepest questions. And alongside these cosmic questions, there's the immediate, practical relationship humanity has with the Sun. Using it as resource, studying it to understand nature, appreciating it aesthetically and spiritually. Solar energy technology captures sunlight, converting it to electricity through photovoltaic panels, or to heat through thermal collectors. Solar power capacity has grown exponentially in recent decades, driven by decreasing costs and increasing efficiency. The Sun provides far more energy than humanity could ever use. Earth receives about 173,000 terawatts continuously, while total human power consumption is about 20 terawatts. Capturing even a small fraction of available solar energy could meet all human needs sustainably, without depleting resources or emitting greenhouse gases. But there's more to solar energy than just Earth-based collection. Concepts exist for space-based solar power. Satellites with enormous solar panels in geostationary orbit, constantly exposed to unfiltered sunlight, beaming energy to Earth via microwaves or lasers. Space-based systems could operate 24/7 without weather interruptions, collect energy more efficiently without atmospheric absorption, and provide baseload power. Technical and economic challenges remain formidable, but the concept demonstrates that the Sun's energy is accessible not just on Earth's surface, but throughout the solar system, potentially powering space-based industry and settlements. And this leads to something equally fascinating about proposals for even more ambitious solar energy utilization. Dyson spheres, or Dyson swarms. These hypothetical megastructures would surround a star with solar collectors, capturing most or all of its energy output. A complete Dyson sphere would be a solid shell, structurally impossible given material science limitations and orbital mechanics. But a Dyson swarm,
millions of independent solar collectors orbiting the star, might be feasible for sufficiently advanced civilizations. Such structures would provide energy on scales dwarfing planetary needs, enabling activities and technologies currently inconceivable. Some researchers propose searching for Dyson structures around other stars as evidence of advanced civilizations, looking for stars with anomalous infrared emissions consistent with waste heat from energy collection.
Whether humanity ever builds such structures remains speculation, but they illustrate how the sun represents not just current energy source, but potential for vast future energy availability. The sun will shine for 5 billion more years, producing energy continuously, reliably, abundantly. Learning to capture and use this energy efficiently could transform human civilization, providing sustainable power for as long as Earth remains habitable, supporting populations and activities limited only by engineering and imagination rather than energy scarcity. Which brings us to the poignant reality that the sun, despite its longevity, is temporary. In 5 billion years, it will leave the main sequence, becoming a red giant, eventually a white dwarf. Earth's habitability will end long before, perhaps in 1 billion years, when solar brightening boils the oceans. This finite timeline raises questions about humanity's long-term future. If we survive as species or civilization for millions of years, a tremendous if, we'll eventually face the sun's evolution, making Earth uninhabitable. Migration to outer solar system bodies temporarily in the habitable zone might provide respite, but ultimately, survival requires leaving the solar system, finding new homes around younger stars, or adapting to live in artificial habitats independent of stellar heating. This far future perspective transforms how we think about humanity's relationship with the sun. It's not eternal provider, but temporary enabler, creating conditions for life and civilization for a limited period before those conditions inevitably change. This doesn't diminish the sun's importance. It remains our life source for the foreseeable future, but it contextualizes our situation within cosmic timescales. We exist during the sun's stable middle age, benefiting from conditions that won't last forever, living in a window of habitability bounded by the sun's past and future evolution. And as you drift now into the deepest rest, your mind releasing its hold on thoughts, your awareness dissolving into the quiet darkness that embraces all things. Carry with you the image of the sun, that golden sphere burning steadily in the cosmic night, converting mass to light, darkness to day, indifference to abundance. It knows nothing of you, cares nothing for your existence, yet it gives continuously, endlessly, the light that makes seeing possible, the warmth that makes comfort possible, the energy that makes life possible. The sun is both near and far, familiar and strange, understood and mysterious, temporary and eternal within its own time frame. It will outlive you, outlive your civilization, outlive perhaps every trace that humans existed, continuing its ancient pattern of fusion and radiation until finally, billions of years hence, it transforms into something new, ending one story and beginning another in the endless cycle of cosmic change. Rest now in the knowledge that whatever comes, whatever changes, whatever uncertainties the future holds, the sun will rise tomorrow morning as it has risen every morning since before humans existed, illuminating Earth, warming the surface, maintaining the conditions that allow life to persist. This continuity, this reliability, this patient constancy provides foundation for everything we experience and dream. The sun asks nothing and gives everything, following the simple physics of fusion and gravity, indifferent yet essential, distant yet intimate, the silent partner to Earth's journey through space and time. Sleep deeply, knowing that the sun continues its ancient work, that morning will bring its light again, that the great cosmic dance continues, stars burning, planets orbiting, life persisting, consciousness experiencing.
all held together by forces as old as the universe itself, as reliable as mathematics, as inevitable as time.